All right, what do we care about? Why are we having this discussion? The reason I bring this up is, this is data I've got, this is old data. Remember when Archie Briggs Road used to be 25 miles an hour? Remember it used to be 25 miles an hour? Maybe you don't. It's okay, maybe you don't. It was my old commute. Before Pioneer moved up, before the Met moved from Pioneer to Grandview Hall, I go up Archie Briggs every morning. Not come up and over the Butte, because it's more direct to get to the top of Grandview that way. I also take some trail that way, which is also nice. But Archie Briggs was my commute to and from work. I still take it home some days, I take it home really quickly. And it used to be 25 miles an hour. It's also one of the more hairball roads in Bend, because people tend to go more quickly than 25 down there. Police will often station themselves at, I believe it's Falcon Ridge Road, which kind of is like halfway down, which is where I got some of this data from, which is actually from police records. The other data I collected kind of by myself. Oh, please, Michael.
I was going to say they have a speed check now.
They do, don't they? That's right. There is one there. You're absolutely right.
Just got put up.
That's it, within like the past week or so. That's right. I noticed there was one of those down on 97, but you're right. There's one on Archie Briggs. Good. I've often wanted to collect data using, like, checking the speeds before. Maybe I'll do that. Because now that it's up, I can put that data in with this data and see. The trick is, though, I really shouldn't, because this data was collected before, right after it changed to 30. Ah, damn. That's okay. You do a face shift on me. Thinking out loud. Apologies. It's 30 now. And it was 25, it's 30, and I'm assuming they put this thing out there to kind of remind drivers to slow down. If they see that they're going too fast, they can think, God, and kind of knock themselves down. It's amazing how accurate those things are. I'm having my Math 105 students right now figuring out the math behind those radar guns. It's actually a lot of fun. Some calculus. I got 105 to calculus. But what are we interested in? The speed limit on this road was 30, is 30. What am I interested in? To see if cars are exceeding. How many tails is this test going to have? If we're exceeding? If we're just exceeding, not if it's different. This is going to be a one-tailed test because we're just going to see if it's exceeding. So what I'm going to do is, I'm going to take in that guy right there. Oh, look, he just kicked in. And I want to put my 5% on the right-hand side and make it a right-tailed test, yes? Yes. I want to see if the cars are landing over in this 5%. So the average I'm looking for is 30 miles an hour. I'm going to compare my data to 30 miles an hour. And if they're exceeding it, they're going to be falling to the right of 30. And if they fall far enough to the right of 30, measured by Mimi standard error, thank you, Mimi. If we get far enough right of 30, measured by standard error, then we're going to go, okay, something's up. We're going too fast. Fair enough? All right. Let's get some hypotheses. Which is the easiest hypothesis to write first? This is my opinion. This is my opinion. It seems to be the best one. Which one? Easiest to write first?
No.
Actually, in my opinion, the research is, but Jack, go for it. What would the null be? What would the null be? No, go for it. What would the null be? Time out. Hold that thought. Hold that thought. What's the variable first? Let's define the variable first. I'm sorry. I should have done this first. What are we interested in? The average speed, go ahead, average speed of cars on Archie Briggs. Okay, sorry. The problem is I define the variable in my head, and I forget that you guys probably aren't doing that just quite yet. You're still in the process of kind of trying to process all of this stuff. Okay, Jack, go for it. Null.
Equal to 30 miles.
Love it. It's equal to 30 miles an hour. What's the research going to be?
Higher than 30.
Very nice. Higher than 30. Laura, what else would we put in the null hypothesis if you wanted to?
The null hypothesis can be less than or equal to 30.
Perfect. Because you're testing it to see if it lands out here. Less than or equal to is everything else. So, totally fine. Your choice, friends. Your choice. Your choice in this. And I haven't checked your book close enough to see if it accepts either one. I will, of course. Okay. All right, our job now, crunch some data. Real quick, we're gonna do two different crunches. We're gonna do neighbor and also police. We'll do them in two different colors so that way they kind of stand out. This will probably raise the end of class, which would be perfect. So let's take a look first. Is the neighbor data first? It is. Let's look at the neighbor data first. If I may, I'm going to take a pause and re-answer Laura's question if it's okay. because your question was so good about if the presence of outliers being existent more in larger than smaller data sets. So here's the deal. In my opinion, it's a function of the standard error. It's a function of how much variance there is in the data set. So I've got the data in L1 and L2 and L1 and L3. Here's the neighbor's data, and here's the police data. Okay, so if I just inadvertently run one var stats, so if I run stat calc one var stats and press enter, I get numbers, but these numbers don't mean anything. These numbers don't mean anything because I didn't count the frequencies that were seen. If I just run one var stats, it thinks there are 7 data points. 17.5, 22.5, 27.5, 32.5, and so forth and so on. Look how big that standard error is. So you've got wide variance of the standard error, which means you have, if you will, you've got lots and lots of wiggle room around the data points, because the data point that's the smallest occurs just as much as a data point near the middle. So you've got this wide variability in your data. If you then realize, oh crap, I forgot to account for the frequencies, and you go one var stats L1, L2, watch what happens to your standard deviation. It has to drop, assuming that the underlying distribution has a shape, because now there are more data points near the center than at the extremes. Does that kind of make sense?
Yeah.
Okay, good. So I accept a lot more variability in a smaller data set. Now, again, outliers are tricky because they are based on a definition of outlierness. For example, yesterday, the one I described for you, that data set that we had a bell curve and a secondary hump, nothing was considered an outlier because there was so much variation in the small sample that everything was within IQR, everything was within 2 standard deviations. But I looked at it and go, oh my God, there's a completely different data set attached to the top of this, and that's the limitation of outlierness. I accept more variation in smaller data sets because you have to. It's just what's going to happen. You're going to have more buckshot scattering in the random samples. So it's a tricky question to answer, honestly. I expect way more variation in smaller data sets. As such, the mathematical definition of outlier won't kick in as much, but that doesn't mean that there aren't some that are clearly different. That's why larger data sets, as long as they're done randomly, are better, because you'll see more of the underlying shape.
Yeah, that makes total sense.
Good. Thank you, my sister. Now, let's take a look at the data. Same thing, plot 1, plot 2. Plot 1, plot 2, but let's change the frequencies to L2 in both of them. So we're looking at an actual mathematical look at the neighbor's data. L1, L2. L1, L2. And then just do a zoom stat. Whoops. Zoom stat. There they are. Okay, I'm going to go. I'm going to mess with the window a little bit to get a better look. I'll go 15 up to, what was that maximum speed? Oh, here it is. 50, so I'll go 15 to 55 by 5s. Yeah, by 5s. And I'm going to mess with the window a little bit more. Make the Y max a little higher. There we go. Now again, that looks like an outlier to me, Laura, doesn't it? That guy right there looks outlierish. It's not showing as an outlier, but it looks to me like an outlier because it's definitely away from the rest. But my point is, if we collected more and more data points, I'm guessing that would get swallowed up by the shape. And that's what I'm getting at. I always see stuff like this in small data sets, but it doesn't register as outliers by the definition of outlier. You see actually more mathematical outliers in larger data sets because the variation shrinks down and more pop out. So this, although it looks like an outlier right now, might be well within the normal bell curve that we're just getting an incomplete picture of.
Right.
Is that fair? I think I confused you earlier with what I was throwing around the definition of outlier, how I perceive it and how it's measured. So mathematically, you're going to get more on larger data sets because the variation shrinking, which is what you said originally. That's what your claim was originally. I would expect to see more outliers on larger data sets.
No, I mean, I'm fine. I get
Okay,
yeah.
it was such a good question. It really is such a really good question because those outliers do color the way the data set looks. It's just that when you have incomplete pictures like this one, that looks like a bell curve to me, doesn't it? it looks like it's missing a bar, but it's also looking like we'll pick up that bar at some point if we get more data, So that's why these tighten down as this gets more full out. But no outliers, right? Nothing's probably unusually pulling the data. So I think we're ready to test. I think we're ready to test to see if the cars are exceeding. So let's go stat tests, t-test just like before, still a t-test. All right, we got to adjust all this stuff. We got to adjust the null hypothesis to 30 because we're tested against that. We got to adjust our listed frequencies to L1 and L2. And we got to adjust our research to greater than, because we're trying to see if they're exceeding 30 miles an hour. Fair enough? All right. Let's draw this. Let's draw this. If we expect area, it'll show on the right-hand side. Oh, there's some. There's some right there. So there's our test statistic. We are about 2.4 standard deviations above, so by the neighbors, we get a t-statistic of 2.4 standard deviations above that carries a big P value of less than 1%. Looks like about 1%. I'm going to call it 1%. Based on the neighbors' data, what do we think? Based on the neighbors' data, what's happening with these cars?
They are exceeding the speed.
Based on the neighbors' data, it appears they're speeding, doesn't it? Based on the neighbors' data. Now, I'm going to throw the histogram back up again. I'm going to throw that histogram back up again. I'm going to finagle the window again. Remember, the speed limit is 30 miles an hour. 30 miles an hour. 15, 20, 25, 30. There's 30 right there. There's 30. So just looking at the raw data, you're like, oh my God, more than half of the sample is speeding. Sure, on average. But when you actually adjust it and look at past just the sample and adjust it for standard error, it becomes that significant over there. It becomes that significant. So based on the neighbor's data, cars are speeding. Fair enough? Believable? In other words, there's no reason to think they're going 30. It looks like they're going more than 30. 2.4 standard deviations above 30. Which on average, now notice that the results didn't give you an average, did they? When we ran the t-test, it didn't come back with x bar equals. You can get that if you need it. If you ever want to see what the sample average is, you can either run one of our statistics, or you can run the t-test with calculate versus draw. And if you do it that way, you'll actually get the sample average. Now take a look at the sample average, friends. 31.6. So they're speeding. This goes back to Jesse's point from a few weeks ago. They are speeding. Oh, I didn't do it right, did I? Oh, I did. I did do well 1 on 2. They're speeding. They're speeding at 31.6 miles an hour. It's above 30. But the question is that practically significant? I don't know. Is it statistically significant? Yes. Yes. Because when you take that 6 and you adjust it for the sample size of 83, it becomes statistically significant. This is where we get into arguments that I don't want to get into. It's only 1.6 miles. It's 2 miles an hour of the speed limit. Nobody gets a ticket for that. The cops won't give you a ticket until you're 5 over. Not the question I'm asking. Are they exceeding 30 miles an hour is the question we're asking. Measured. How about the cops' data? How about the cops' data? Do the exact same test, but use the cops' frequencies, L1, L3. Exact same test, L1, L3. And see what that looks like. Let's draw this one. We'll draw this one. We're still going to be looking for that right area, the right area up there. Oh! Uh-oh. Cops. 0.57 standard deviations. Just about a half of standard deviation. P-value. About 29%. What's the cops' conclusion? Was it actually saying no? Jack's saying no. It does not appear that anybody's speeding using the police data. Now wait one damn minute. How can that be? How can that be? They're clearly going faster than the speed limit because they're to the right of 30. And if I run one of our stats on L1 and L3, we got an average of 31. It's not the same average as it was in the neighbor's data, wasn't it? It was 31.6, 31.1. It's still about a 1 mile an hour over the speed limit. How can it be significant with the comp data or significant with the neighbor's data and not be significant with the comp's data? How can that be?
I don't think they used a big enough sample size.
That's it. It all goes back to Mimi's measure of the standard error. Because the police only use 15 data points, they have to accept a wider margin of error, which means the same 1.1 or 1.6, whatever it is, miles an hour doesn't travel as far away from average when viewed from a standard error point of view. It travels a lot further when you have 85 data points like the neighbor did, versus when you only have 15 data points like the police did. Exponentially higher. Actually, not exponentially, multiplicatively higher. That's the big difference. And that's what's kind of cool. Depending on whose data you use, they say two different things. Does this mean statistics is crooked? Of course not. It means it depends on your sample size. I mean, that's really what it depends on. A larger sample size will generate more precise results. They're both centered on the same value, as they should be. The central limit theorem guaranteed that at any sample size. What the central limit theorem also guarantees are tighter curves. So essentially, what happened, to wrap this up, what happened was both data sets resulted in an average that landed right here. But for the cops, they landed on this curve. The neighbors landed on that one. Same distance from 30, but totally different distance when viewed from the idea of standard deviation. Cool? Alright. Don't do any homework for this yet. I got a whole bunch more data sets I want to play with in class on Thursday. So I sense we're getting there, but we're not quite 100% comfortable yet. And I do want to play with some more data sets. I've got some data sets I want to collect from you guys. So project and not quiz out. That's good practice. Yeah, what's up? Can one of you guys turn the camera off? That'd be great. Save the battery.